well, so what do I want to talk about today? So I guess my understanding is that in the seminar, you guys have been, at least in part, working through Nakajima's book on Hilbert schemes. So in particular, the Hilbert scheme of points on C2 is something that you've studied, and in particular, the Hilbert-Chow morphism from this to the nth symmetric product of C2. So this is the fact that this is a resolution of this space is something that we kind of already have. So the theme of today is going to be, well, okay, if you take a finite subgroup of SL2, then we kind of want to understand something, at least, about inputting the action of such a finite group into this picture. So in particular, by virtue of the inclusion into SL2, the finite group gamma acts on the plane and acts on everything in sight here. So certainly by acting on C2, you get an induced action on unordered M tuples of points on C2, and certainly, and then also on the Hilbert scheme of points on C2, and this Hilbert-Chow morphism is equivariant for that action. So this is the picture we want to start understanding a little bit. So what do we want to understand about this picture? So there may be two goals to try to explain. So the first is, well, in the study of finite subgroups of SL2 and in the Mackay correspondence, one is interested in the associated simple singularity. So this is the space of gamma orbits on C2. So this so this is a simple singularity, and it has and of course one can think about this maybe somewhat analogous to this space and ask about some version of some resolution of it. So let me actually move this guy, the non-singular guy. This down here is the simple singularity, and so this is a picture. The resolution of the simple singularity is something one cares about in a few places, including the Mackay correspondence. So one can ask what this kind of resolution has to do with this Hilbert scheme of points on C2 and the Hilbert-Chow morphism and the action of gamma. So the first goal of the talk is going to be to explain how to recover this resolution from this picture. That's the first goal of the talk. And then the second goal of the talk is to explain how this Hilbert schemes of points on C2 perspective on this resolution allows you to recover the Mackay graph. So you sort of, so I'll be more precise about what I mean by this when we get there. Okay. All right. So okay. So the first thing I want to do again is I want to take this picture and produce from it a resolution of the simple singularity. That's what we want. Okay. Okay. So let's do that. So here, to do that, what we want to do is let's let M be the order of the finite group gamma. Okay. So immediately we're going to restrict, and we're going to consider the Hilbert scheme of M points on C2, where M is the order of gamma. All right. So let's look at so the first claim, which we want to think about, is that if I look at the mth symmetric product of C2, Okay, so gamma acts on C2. So gamma acts on configurations of points in C2, the M-symmetric product of C2. And so I want to understand what are the gamma fixed point components of this. So the first claim is that this is a single component, a single connected component, and it's just isomorphic to the space of gamma orbits on C2. Okay, this is the first claim. Is that yes? Oh, good. So maybe I won't write it down. Yeah. Okay. Good. Yeah. So what's the point? The crucial fact here is that the gamma. I'll just say it out loud. The crucial point is that the gamma action on C2 is free outside the origin. Okay. So if you took a point in the symmetric product, a point in the symmetric product is an m-tuple of points in C2. Just look at one of them. If it's non-zero, then being fixed by gamma means the entire gamma orbit is in there. But m was the size of gamma, so that the entire m-tuple is exactly one gamma orbit. So if one of the points is non-zero, then all the points are non-zero and they're precisely a gamma orbit. On the other hand, if one of the points is zero, there's not room for a non-zero gamma orbit in m points, so all the points have to be zero. So it's in this way. This space is the non-zero gamma orbits union a single other point, zero. Okay. Any questions or comments about that? Okay. So all right. So that's the downspare space. So let's. So now we get here again, and this is very important. I mean, it's interesting to think about this story when m is not just the order of a gamma, but for the moment we'll restrict to that. So. Okay, so now upstairs. So now the second thing we want to consider is, so now we consider the upstairs story. So the gamma fixed point components of the Hilbert scheme. So unlike the situation here, this is not connected. So this has a bunch of different connected components. So in fact, we'll be interested in a single connected component of this space. So okay, so let's study that. Did you say anything about this? No. Okay. Let's see. So how do I want to say this? So here, this is yields J in the polynomial ring, so that the dimension of okay. So associated to an ideal J, you have this finite dimensional vector space, and if the point J is actually fixed by gamma, then this space, let me call it N for a second, this naturally has the structure of a representation of the finite group gamma, so a module over the group algebra. So this is a module. So the connected component, well, so the the subset in here that we're interested in for the moment is the subset consisting of those gamma equivariant ideals where, as a C gamma module, this is the regular representation. Okay, so in general, if you're an invariant ideal, then you get this representation of gamma, decomposes however it decomposes. We're particularly interested in, so consider J such that J is isomorphic actually to the regular representation. It's a module over okay. So okay, so the claim, the next claim is that so I'll just write here, this space is actually a resolution of C2 mod gamma. In particular, if you take the Hilbert-Chow morphism and you restrict it to the gamma invariant part, then in the base you just have this space, and that restriction is a resolution, and that resolution is one connected component of the pre-image is exactly this. Okay, so you guys haven't talked about this part of things at all. Okay, so I mean I think the easiest part of this to see so what part of this is easy to see? So we have the Hilbert-Chow morphism, which is a resolution, and then yes. All right. All right, that's a reasonable request. Okay, so so if we take, so inside here, of course, we have as we explained, we have the simple singularity, and inside here we have so the stratification here. Remember, there are two strata here. There's the locus, the open locus, where the point is non-zero orbit of gamma on C2, and then there's the origin. So let's look just at the open locus, C2 on gamma minus. Okay, so that lives inside. Well, so M is the order of gamma, right? So if you just look at a gamma orbit, forget that it's a gamma orbit. It's just an M tuple of points in C2, but it's an M tuple of distinct points in C2 because the gamma action is free outside the origin. Okay, so this open stratum in here sits inside the stratum of the symmetric product consisting of M distinct points, right? And I mean, hopefully this is something you guys at least mentioned before, but this is the Hilbert-Chow morphism is an isomorphism over this open stratum. Okay, so if you look at the preimage of pi over the stratum, that map is an isomorphism. Okay, so you get that if you so you immediately get that if you look at, so this is not the entire simple singularity, this is just the complement of zero. But if you look over the Hilbert-Chow morphism over the complement of zero here, that's an isomorphism. Okay, Okay. So we already have that. So the only other thing we need to check is that the main other thing we need to check is that the gamma fixed points over here are themselves non-singular. Right? So we have in other words, we have. I'll erase everything and stay here for a little bit. So what I'm trying to argue right now is that well, so what do we know? What we just argued is if you take the complement of the origin and you take the Hilbert-Chow morphism and you restrict it, this is an isomorphism, right? And this, of course, sits inside here. Well, maps to here. So the point is that this is supposed to be a resolution. I mean, if I pick the connected component, I mean, take the connected component in here that contains this. Then I just need that connected component is smooth, so that this is a resolution. So Y is the connected component of the gamma fixed points on the Hilbert scheme, the component which contains this. So why is this smooth? And that's just because the Hilbert scheme itself is smooth and gamma is a finite group. So if you have a finite group acting on a smooth space and you look at the fixed point components or a finite group action on a smooth space, then those components themselves are smooth. Okay. Okay. So that basically, that's the basic explanation of why if you take the Hilbert-Chow morphism, and then you restrict it, you get a resolution of the simple singularity. So that resolution can denote like this.
Tony, Anna says you can hear me. Can I ask a question?
Yeah, Peter can ask a question, yeah.
So your definition of the resolution involves this quotient being the regular representation. Can you give some example of a fixed ideal where the quotient is not regular?
Sure. So the question is, can I give an example of a fixed ideal where the quotient is not the regular representation? So yeah, let me think for a second. So, okay, great. Well, Anthony remembers one with n equals. So what can you?
So I think it's so I'm thinking about gamma being the cyclic group over 3.
So let's okay. So let's. So gamma is cyclic group over 3.
And I think if you take the ideal generated by x cubed. Sorry, that's in the regular group, but it's the ideal generated by x squared,
X squared, xy, sorry, and y squared. Okay, so let's see. Can we see why? So we want to look at this. We want to look at this representation of the cyclic group of order 3.
Is the generator of Z3 acting by the same scalar on x and y?
No, it's acting by inverse scalar. The generator of Z3 is acting by inverse scalars on x and y. So, okay, yeah.
So Z4
Okay, so we're gonna look at the
also
sigma.
calculate the xy for the ideal. So the basis for the quotient is 1 x, y, and xy.
Okay, so if we take gamma as the cyclic group over 4 and look at the ideal generated by x squared and y squared, then Anthony's claim is that the quotient is spanned is a vector space basis of this is what? So,
1 x, y, xy.
great. Okay, and the definition of the cyclic group action is on C2 is, you know, it's inside SL2. It's like this. So the point is that if gamma is little gamma is a generator of the cyclic group, so it's a fourth root of unity, then x is scaled by gamma and y is scaled by gamma inverse. So if you look at the gamma action here, it's got 2 copies of the trivial representation. Good. Okay. So the upshot of this, well, one upshot of this discussion is that you get a moduli interpretation of the resolution of the simple singularity analogous to the moduli interpretation of the Hilbert scheme. So that's one offshot, which I want to write down. So okay, so let me just say that in concretely. So we know the Hilbert scheme of M points on C2 is ideals of codimension M. So now we get from this a similar kind of interpretation of the resolution. So now we have to think a little bit more. So these are going to be some gamma invariant ideals. So let's write it down. So this is J such that J is gamma invariant, and the quotient is isomorphic to the group algebra as a gamma module. Okay, and okay, so this is one thing you get, and you can rewrite this. So let's see, how do I want to rewrite this? So one thing which is nice to do is to instead of separately, so what kind of structure does this space have? Let me call this N for a second. It's a module over gamma, but it's also a module over the polynomial ring. So really, it's natural to just put them together in this case. And so this is what I want to do is I want to write this down as a moduli space of some of these representations N. So this is N. We're here N. Now, what is N a representation of? N is a module for the smash product of CX, Y, and gamma, right? Gamma acts on here. So you put the gamma action and the polynomial ring action together. This is like a semi-direct product. So this is, you know, at the vector space, this algebra is just a tensor product, but the algebra action is twisted in that it involves the action of gamma on CX1. Okay, so then this resolution is N modules over this ring, such that what? Well, so there's 2 conditions. So this gets translated into 2 conditions if we want to describe it as a module over this ring. So let me see if I can remember that. So the first is that N is isomorphic to the group algebra of gamma as it just as a gamma module. But the second thing, so what's special about these kind of quotient modules over this ring they're generated, they're cyclic modules. If you just take the vector 1 in the polynomial ring and you act by gamma and polynomial rings, you get everything, right? So n is generated by a single vector v, and that single vector v spans the trivial module component of n. So this is going back and for these two descriptions. Let me write it on the page. So I'm not saying anything particularly deep here. I'm just saying you can go back and forth between thinking about ideals J in CXY or quotient modules CXY J. These two descriptions are meant to say you can go back and forth between those two things. I mean, that's a condition which, so in general, that's a condition. If I just looked at, I could just look at modules over this algebra, which are isomorphic to the regular representation of gamma as a gamma module. That's something one could consider. That would be bigger than just this space, because here the modules we're considering are of a very special form. They're quotient of this guy by an ideal, and those guys have the added property that their vector 1 in the 1 in here generates the module. Yeah. So if you that's right. So I feel like I haven't explained that sufficiently. I mean, you want to? Yeah.
There's a slight sort of difference between the two lines in that the first one is sort of an actual set in some sense, and the second one is meant to be isomorphism classes.
Yeah, that's right. I mean, yeah, it's a good point. I mean, yeah, I mean, I'm claim so. Yeah, that's an excellent point. But the main point I just wanted to keep in mind that you can think about the ideal in here with its, or you can think about the quotient, and you can go back and forth between the two. Okay, and that's important because when we talk about the Mackay graph in a minute and how you get the Mackay graph, I think it's cleanest to say things by thinking about representations like this. Okay, so you know, you want to keep something in your head. This is a moduli space of representations of smash product of the polynomial ring and the finite group. And you want to know exactly which moduli space, then we have to say some words, but this is the important point to keep in mind. Okay. Okay. So so that's what you get. This is maybe a thing to keep in mind. That's what you get from thinking about the Hilbert scheme of points on C2. I mean, certainly this resolution one was studied before it, so you don't need the Hilbert scheme to talk about it. You can talk about it independently. But one thing you get from the restricting the Hilbert-Chow morphism to gamma is you get a statement like this. You can think about the minimal resolution as a moduli space of representation. Okay. Okay. So now I want to talk about from this point of view how to get the Mackay graph. The next goal is It's something about the Mackay correspondence. I mean, I'm just going to talk about how to recover the Mackay graph. It can mean something much richer, which maybe you guys will talk about later. I don't know. So in particular, well, let me just state the let me state the theorem and then we'll explain it. So the procedure here is we're going to start with this moduli space of representations, and we're going to produce the associated Dynkin diagram. So the finite subgroups of these gammas are in an ADE classification, so they're in bijection with the ADE Dynkin diagrams. I'm going to explain how to recover that ADE Dynkin diagram from here. And okay, so that's the kind of question. How to recover the associated ADE Dynkin diagram. From, well, in particular from the moduli space description of the resolution of the simple singularity. And one formulation of this, which I guess I was aware of before, but that Anthony reminded me of recently, is one very nice formulation is due to Crowley-Bovey. So I want to explain to you his description of how to recover the Mackay graph. Okay, so let me give a sentence about the starting point here. So if you like, maybe I just wrote this down a bit more cleanly. This is supposed to be one of the things we got from the first part of the talk, is that the resolution of the Kleinian singularity is a moduli space. It's a moduli space of representations of the polynomial ring smashed with the finite group gamma. So if you look at modules for the smash product with two conditions. So the first is that if you just forget the polynomial ring action, if you just look at the gamma action, it's the regular representation. Okay, so if it's the regular representation, then of course, if you take that module and you hit it with the idempotent for the trivial representation, that's going to be a one-dimensional space, because the trivial representation appears with multiplicity 1 in the regular representation. And so the second condition on the modules is that this module is generated by the trivial component. Okay. Generated as a CXY smash gamma module. But yes, but yes, that's generated as a CXY module. Yeah. Okay. Okay. All right. So now that what I want to explain is how to get the Mackay graph from this story. So let me remind you what the answer is supposed to look like. So if you so this statement predates Crowley-Bovey's interpretation of it. So if you look at the exceptional fiber, so you look at the pre-image of 0 in here, then the exceptional fiber of this resolution is has some irreducible components. Those irreducible components are all P1s. They're all complex projective lines. And if you look at any two of them, they're either disjoint or they intersect at a single point. So this is a union of I'll say what this means in a second, of P1s, and if you take the intersection, well, it's either empty or it's a single point, and the the combinatorics of when these guys intersect is given by the ADE Dynkin diagram. So here, let me just say what that is. So let's say I is the set of irreducible representations of the finite group gamma, and 0 denotes the trivial representation. So then if you define a graph G, whose vertex set is the non-trivial irreducible representations of gamma, then this set, the non-trivial irreducible representations of gamma, is in bijection with the irreducible component here. So you're going to have one irreducible component for each non-trivial irreducible representation. And if you draw an edge between the vertices when the components intersect, then that gives you an ADE Dynkin diagram. So the edges, you put an edge from I to J when the corresponding irreducible components intersect to non-trivial. When they intersect. Okay, so that's the combinatorial picture we want to recover. So the question so the way I want to describe it, I mean, you could ask, it's reasonable to ask, under this moduli interpretation of the resolution of C2 mod gamma, what are these irreducible components? So what are these E sub i's? And how do, and when they intersect, you know, what is this point? So this point is some distinguished representation of the smash product. All the points here are. So that's the question which Crawley-Bovie asks and answers, and I want to tell you what the answer, what he says. Okay. Okay. And again, the paper is on the exceptional fibers of Kleinian singularities. So I'll give you the answer and then start telling you a little bit about the proof. And there are many details in the proof that I haven't learned myself. So I'll try to give you the structure of at least the outline, and then if there are some points we want to talk about more, we can talk about them. Okay, so I need a little bit of notation. So remember, all everything in sight here is a representation of, so all the points in the resolution are representations of this algebra. So okay, so let's so for I an irreducible, so let's say so let's say for Ni, an irreducible representation of the finite group gamma, let's let S sub I be the irreducible representation of the smash product, which is just, as a gamma module, it's just Ni. And I've extended the action here by just letting X and Y act by 0. And the XY X and Y act by 0. So this is some distinct, so of course, you know, there's finitely many irreducible representations of the finite group gamma. If you inflate them to representations of this entire guy by having X and Y act by 0, you get some irreducible representations of this big ring. Let's call those SI. Okay. Now if we're given if we're given a point in here, so that's, again, I'm thinking about that as a representation of this ring now. I want to let, so what we can consider is we can consider the SOCL. So this is the sum of all the simple submodules of M. So M is some representation of this guy. So we can look at all the simple submodules in there and take their sum. That's the SOCL of M. So so in particular, we can consider all the modules M whose SOCL contains this particular representation SI. So let's let the I be M such that the SOCL of M contains the distinguished irreducible representation SI. Okay, so this EI is a possibly empty subset of solution. So the theorem, this is Crowley-Bovey's theorem, is that these EIs are the P1s that give you the Mackay graph. Okay, so for I non-zero, so I'll say which means just that the irreducible representative of gamma is not the trivial module. This is a P1 sitting inside here, and so EI intersect EJ is either empty or a point, and it's empty when I and J are distinct vertices which are not connected in the AD-Dinkin diagram, and it's a point precisely when I and J are connected in the Dinkin diagram. Okay. Say for I equals 0, yeah, that's a good question. So let's look at what E of 0 would be. I mean, it's defined there. So anybody have a guess or so I'm really thinking about not just arbitrary modules, but modules in here.
E of 0 should be empty.
Yeah, that's right. Peter suggests that E of 0 is empty. It is. So the reason E of 0 is empty, so points in E of 0, if you had an M in here, that would mean that the SOCL of M would have to contain this S0, which in particular, as a gamma representation, is the trivial module, right? But one of the conditions on M in this moduli interpretation is that that trivial representation generates the entire module under the action, right? And so the only possible module which is generated by S0 and contains S0 in the SOCL simple subs, is just S0 itself. So the fact that these guys all have dimension vector, they're bigger than just the trivial representation. So the trivial component can't be a simple sub. It's got to map out to other things under the action of action 1. Okay. So in fact, that's right. So so E of 0 is empty. So in particular, part of the claim here is that, you know, the other ones are non-empty. Actually, there's a P1's worth of them, and there's this intersection. Okay.
Tony, can I just
Yes.
ask a bit about the meaning of the connection in the Dickey diagram? I mean, you haven't. So the only sort of meaning this can have at the moment is that the edges you're talking about are the ones in the K graph.
Yes.
So the connectedness condition is about whether NI is contained in the test product of C2 and J.
Yes. Yeah. So let me reformulate that graph. So yeah, you bring up a good point, which is so. Yeah. So Anthony points out that I haven't defined this graph except to say the McKay graph, which so I should, you know, I haven't specified what this condition means in any language other than saying the McKay graph. So let me say what this means in the language of roots, since that's slightly more natural for the proof. I mean, this is meant to be connected in an ADE Dinkin diagram connected to gamma by the McKay correspondence, but let me. So so the graph, maybe one. So associated to maybe we have to take something as a little bit of a black box here. So associated to the finite subgroup gamma, there's a root system of affine type. So type. So in this root system, there are so from this point, from the point of view of the root system, this root system has simple roots some collection of simple roots, and it also has a pairing on it. So the pairing of alpha I with alpha j is 2, if alpha I with itself is 2. Sometimes the pairings are -1 and sometimes the pairings are 0. So these are the options for the pairing on simple roots. So if you draw a graph, so the affine type ADE Dinkin diagram arises from taking a vertex for each simple root and an edge from vertex I to vertex j when the pairing is -1. So indeed, this graph can be reformulated in many different ways, but this is one way to formulate it.
The primary meaning of the vertices of the set capital I is that it's the set of reduced representations of gamma. So, I mean, is it any easier to define the root system in those terms than it is to?
No, I mean, I guess, yeah, I guess I'm taking as a black box the fact that there's a bijection between simple roots in this root system and irreducible representations of gamma. Yeah. So I mean, I don't know what the. That's right. So there, I mean, there's a bijection here, the simple roots and the irreps of gamma. And I don't see how this particular moduli, I don't see how this particular moduli interpretation of the resolution sheds any direct light on that. That's a reasonable question.
moment with K correspondence in purely representation theory terms.
Yeah.
I mean, I think if you interpret the connectedness relations there in those representation theoretic terms, then this theorem has real content. It tells you that that representation theoretic graph is the same apart from the extra vertex as the graph of your individual components of the resolution.
That's right. But I think, you know, if you look at Crawley-Bovey's proof, I mean, so I'll say something about it in a moment, but the basic tool in this, in his theorem is a connection between representations of the algebra, the polynomial ring smashed with the gamma, and the root system. Like the basic question you want to know is when can you, like what can you say about the decomposition? You know, have the regular representation. What can you say about the Sokal of the opposite there? So it really does connect directly to the root system. Yeah. Yeah, it's a good point. I don't think I have an answer organized well enough in my head to answer it. Yeah. Okay. So let me state some propositions which shed some light onto why you get this kind of result. Lemma. If so let me for a second. So let's say you have a module and let's suppose now, I mean, we're studying the Sokal of M, so we want to understand what are the simple submodules of M. And in particular, in the definition of this set EI, we're interested in studying modules M so that this trivial module SI, where X and Y are acting by 0, appear. So there are many modules here that are not in any of these EI, where none of the Sokal of this guy will not have any copies of SI. But we want to understand some restrictions on what kind of SIs can appear. So let's suppose that the Sokal contains two modules, SI and SJ. Okay. Then, well, first of all, I does not equal J. By that, I just mean that SI does not appear with multiplicity greater than 1. Does not appear with multiplicity 2. And moreover, I and J are connected in the graph. In other words, the corresponding simple roots are paired with -1. So in other words, if you just think in terms of pictures, if you think about the vertices of the Dynkin diagram, if you take two vertices that are not connected by an edge in the Dynkin diagram, each of those vertices corresponds to a module SI and SJ. There's no module, if those vertices are not connected, then there's no module in here that has both SI and SJ in the Sokal. Okay. Moreover, if you have two vertices that are connected, and there is a unique M in here, such that the Sokal of M contains Si plus Sj. In fact, it's equal to Si plus Sj, but that's so important. So this uniqueness statement, this is together, this is giving the statement number 2 here, right? It's saying there's nothing, if I and j are distinct and not connected by an edge, then there's nothing whose Sokal has Si and Sj. In other words, this intersection is empty. And moreover, if I and j are connected in the diagram, then there's a unique module. So this intersection is a single point.
Oh, I had a question too.
Sure, Peter has a question too. And Peter, you go ahead.
Does Crowley-Bovey like prove that this intersection is transverse, or is he just looking at the set theoretic intersection?
No, he does not. Peter asked if Crowley-Bovey proves that the intersection is transverse, or if he just looks at the set theoretic intersection. I don't think he addresses the transversality of the intersection at all. It's just set theoretic. Yeah, he does. He does address this isomorphism as an isomorphism of varieties, not just as a set theoretic isomorphism. Though I haven't looked carefully at that. I just looked at the set theoretic isomorphism here. Yeah. So the question for those of you who didn't hear is which simple root corresponds to which SI, right? So, I mean, a root system, I mean, in particular, that's a free abelian group with a pairing on it satisfying some conditions, right? So the statement is really that you can start with one version of the statement is that you can start with the SI and you can construct from it a root system where the simple roots are in bijection with the SI. So you construct something that has the axioms of a root system, and then it is whatever root system it is. I don't know if there's a more direct way to say it. I mean,
yeah, that's what I would say. I think that's what Lustig does as well. Usually, it starts with the group. The text is the set of reducible representations of the group. You define whatever lattice or pairing.
Yeah. So in particular, maybe it's worth saying in terms of these SI, that pairing has a very natural interpretation. So let's just say I take if I take a free Z module spanned by a vector for each SI, I mean, that's just a free abelian group right now. I want to put a pairing on it. You can use the Euler form in the category of, if you're thinking about the category of modules over this algebra, you can use the Euler form on there. So you can define for whatever, I'll just define it on the SIs. Equals, the dimension SI Sj minus the dimension of x1 SI Sj plus the dimension of x2 SI Sj. This turns out to be symmetric in I and j, and this is either so this is 2 when I equals j, it's -1 in some cases, it's 0 in some cases. And then one proves that this is a root system whose simple roots are these classes SI. And so then the bijection is whatever it is, and yeah. Okay. Okay, so this is one half of the Crowley-Bovey statement, that This is telling you that the intersections are empty or a single point. And then there's a second part of the statement, which is that the EI itself is a P1. Both of so to really completely give proofs of that is not something I'm capable of doing, but I do want to tell you what the kind of main tool in these kind of statements is, because that main tool is really interesting, and that's where the connection to root systems really comes in. So, so if you're given, so let me introduce a little bit of notation. So given a module here, then M is, of course, you can just forget about the action of polynomials in X and Y and just regard it as a module for the group algebra of the finite group. And so as a module for the group algebra of the finite group, it decomposes into irreducibles, and this here is the multiplicity space. Okay, so let me define the dimension of M. This is underlined. This is Crowley-Bovey's notation. This dimension vector. So I'm going to view it as an element in the root lattice of the corresponding root lattice by taking the by just taking the coefficient of the simple root alpha j to be the multiplicity of the corresponding irreducible module. So that's kind of a mouthful, but the idea is fairly simple. This is a module over a big algebra. Just forget everything but the finite group action, decompose it, and look at the dimension vector is just the multiplicities of the various irreps. Okay. Okay. So so then the yes, excellent point. So in this case, it would be the regular representation, but let me not just think about it for these. Let me think about just any finite dimensional representation over this algebra. Yeah, that's a good point. That's actually important in this statement. We'll use situations where this module is not in the resolution. Okay, so then here's I'll just put it as fact. This is where a lot of the work happens in Crowley-Bovey's theorem. So the possible dimension vectors for okay. So yeah, okay, fine. Okay. So suppose I want to make one further assumption on the kind of modules that we're considering. Suppose M is cyclic, meaning that, let's just say, like in the situation we're studying, that that the dimension of the trivial representation is 1, and this component generates the entire module. And M is generated by EM. Okay, where E is this trivial idempotent. Okay, then the possible dimension vectors for modules are highly constrained. Okay, of course, if I didn't put some condition on the modules, then there would be no constraints on the dimension vectors because you could just take direct sums of SIs and get whatever you want. But those direct sums typically won't be cyclic like this. So if you have the module being cyclic, so if you have some distinguished vector which generates everything, then the dimension vectors are quite constrained. Then in fact, the dimension vector of M is a positive root of the root system where everything is living. Okay, this is an affine ADE root system. This is a positive root. Good question. So let's see. So you can prove that statement by induction on the dominance order in roots. So let's come back to this. That's a good question. I mean, that's not in Crawley-Bovie's paper. That's, I mean, precursor for Crawley-Bovie's paper. It's also worth saying, though, I'm not writing it here. Crawley-Bovie doesn't really spend much time phrasing things in terms of this algebra and modules over this algebra. He works with a Morita equivalent algebra called the pre-projective algebra. And these dimension vector statements are maybe a little bit more natural in the language of the pre-projective algebra. That's right. That's right. Yeah. I mean, not literally, because the pre-projective algebra is about representations of the doubled quiver. But I mean, it's morally part of the same story. I don't know, Anthony, do you have anything you want to? I mean, that's in addressing this question. Yeah, I mean, it's yeah. So this is something we haven't explained. Moreover, the so I mean, we have a root system here. So this root system also has a Weyl group, and the alpha I, which are the simple roots. And inside the roots, there's the Weyl group orbits of the simple roots. These are what are sometimes called the real roots. So if you were in a finite type root system, this would be all the roots. But if you're in an affine type root system, like we're in here, in this root system, there are roots that are not in the Weyl group orbit of the simple roots. The Weyl group orbit of the simple roots is called the real roots. So another fact, which is really connected to this first fact, is that as I said, if you have a module which is then its dimension vector is a positive root. So in fact, if this dimension vector is a real root, then there's only one such module. Then M cyclic is unique. Okay. If so, the roots that are not real are called imaginary roots. I think it's known that if the dimension vector is an imaginary root, then such a module is not unique. I think this uniqueness is an if and only if statement, I think, but yeah. 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 So back to if you think about this statement in Crawley-Bovie's theorem that modules with Sokal I intersect modules whose Sokal contains Si intersect modules with Sokal contains Sj, that's a point. How are you going to prove that statement? You're going to say that if you have that there's a unique module whose Sokal contains Si plus Sj. So let me just say, I mean, hopefully this will give the essential flavor of the argument. So let me So now let's suppose let's suppose that M is in here. So I introduced this dimension. This dimension vector of module in here is not a real root. This dimension vector is an imaginary root. It's typically called delta. Okay, so the this is an imaginary root. Which is good. This space is not a single point, so we wouldn't have expected the dimension vectors to be imaginary. So let's suppose that your M in here has Si and Sj in the SOCL. Okay. So what does that mean? That means that there's some, that means in particular Si plus Sj is a sub. So Si plus Sj is a sub, and there's some quotient. So you get some exact sequence of modules like this, right? So let's look at this N. So this N, maybe I shouldn't call it M. Call it N. I used that earlier. I call it M prime. So let's look at M prime. What is the dimension vector of M prime? Well, by construction, it's delta minus alpha I minus alpha j. Okay. So now you can use knowledge of the root system to say quite a lot. So for example, suppose I equals j. If I equals j, then the dimension of M prime is delta minus 2 alpha I. Well, that's not a root. This is not a root. So there's no such M prime. So there's no such sequence like this. So there's no such module which has 2 copies of Si in the SOCL. Okay, so that's one of Crowley-Bovey's claim that that if Si is in the SOCL, it appears with multiplicity of most 1. Similarly, if I and J are in the Dynkin diagram but not connected by an edge, then this is not a root. So if you take delta, this is something that you have to get one's hands dirty with. So this is, this delta is the smallest imaginary root, so you basically just have to check that this guy's not a real root, and that's not so bad. That's right. Yeah, good. Okay. Okay, good. Yeah. So that gives that fact that, so those two, that immediately gives that EI intersect EJ is empty when I and J are not connected in the Dynkin diagram. Okay. And then, so what about when I and J are connected? If I and J are connected in the diagram, then this is a root, but it's a real root. In other words, if I look at it an exact sequence like this guy is unique. There's only one such guy here. So that's not exactly what Crowley-Bovey's statement is. Crowley-Bovey's statement is that there's one such guy here. This guy is what's unique. This guy would be the guy in EI intersect EJ. So what you know from this root stuff immediately is that this guy is unique. You need to know that this guy is unique. And to take this and to argue that the middle term M is unique, you need to know something about X between Si and M. So So we know, so M prime is unique, we know. So then we have to study I guess we have to study X1 from SIM and X1 SJM.
You mean
And-
X1 of M prime SI?
Sorry, M prime. Yeah, sorry, thank you. So say that again, Peter. What do I mean? So I want to look at X. Yeah, say again, Peter. M prime S1. Is that what I mean?
M prime SI plus direct sum SJ.
Yeah, and X1 M prime SJ. So the claim is that both of these are one-dimensional. And again, it's this root system connection that allows you to see that. If you had two, so first of all, this it's not. I guess it's not hard to see that this is non-zero. But if the X1 were greater than one-dimensional, then you could construct a module whose dimension is not a root. And similarly, so it's again the same sort of root system arguments that tell you that these are both one-dimensional, and then some sort of 5-lemma argument from these X being one-dimensional, and the uniqueness of this allows you to conclude that M is unique. That's the idea. Okay. Okay, so the last thing I want to say is a little bit about the fact that EI is P1.
That's surprising to me because usually when you have,
Hold on, Peter's asking.
often when you have a two-dimensional X1, you don't get a unique middle term. It's not formal.
Well, but we're not. I mean, yeah, I agree.
So there's obviously something going on.
No, I think this is. Let me think about it for a second. I mean, I'm pretty sure this is how the argument goes. I mean, Peter is claiming that it doesn't, Peter's claiming that it's not a formal consequence that these guys are one-dimensional. But
sum end is a direct sum. That has to appear, I guess. All I said is you have to use the fact the sum end is a direct sum somehow if you want it to be formal. The submodule is a direct sum.
Yeah, but so Peter said you have to use the fact that the submodule is oh, you mean that the submodule is a direct sum here?
Yeah.
Yeah. Yeah, I don't, sorry, I don't see, I can't come up with the argument on the fly. I see your point though. Okay, so let's say, I mean, let's just look at what we have. We have, let's look at isomorphism classes of short exact sequences. So what Peter points out that I think we all agree with is that if we look at isomorphism classes of short exact sequences like this, that's two-dimensional. This is a two-dimensional space, but that's not exactly what we're interested in. What we're interested in is isomorphism classes of M. So there's of course an equivalence relation on short exact sequences, which is we declare two short exact sequences of this form to be the same if the M in the middle is the same. And so if you have two such guys, they have the same M prime. You can rescale here, and you have a two-dimensional. You have C star cross C stars worth of rescaling. there on the maps from SI to SI and the maps from SI to just SJ. So this two-dimensional space, that C star cross C star should chop down the isomorphism. I think that was Anthony's. That was your suggestion, or this? Yeah, that's Kevin's idea. Does that sound right? Yeah. I think a similar sort of thing, maybe a similar sort of confusion. Let me just finish by saying where we get the P1, because maybe a similar sort of issue is going to arise. Okay, let's see if I can remember where we get a P1. So the claim is that EI is P1. So EI, remember, is M such that SI is contained in the Sokal of M. Now, I think once again, one computes that X1 of M SI is one-dimensional. I think that's, so I'll say something about that in a second. And that's again a root computation. If you have an extension of, so if you extend M by SI, that's a real root. So there's a unique extension of M by SI, just because the dimension vector of M plus SI is a real root. So that extension, I don't know, let's call it L, fits into an exact sequence like this. And the point is, so the point, I think the point is that, so the dimension of, if you take an M and you extend it by SI, no matter what M we take, the dimension of this L will be the same, and that's a real root. So no matter which M we take with SI in the Sokal, this L is the same for all the different M's. That's what the fact that delta plus alpha I is a real root gives us. Okay. So well, I want to take M and I think I want to extend it by SI. I mean, it's true that that's also uniquely determined independent of M. So we have to study, okay, so then, okay, okay, so now I want to know what's the dimension. Now I want to know what is Halm from SI to L. So the claim is that this guy has dimension 2. Okay, and that again follows from this is what Crawley-Bovey calls a homological formula, which is just basically the fact that the Euler form is the pairing on the root lattice. So, okay, so I'll say more about this if somebody wants, if I have to think about it for a second. But this is, so once you have this, what's the point? Once you have this, Halm SI is 2, then we've described M as a quotient of L by SI, the same L for all M, right? So in other words, taking this sequence, this sequence to its co-kernel gives you a map from the space of M's to this P1. Okay, so this gives, that's how you get a map. So you get a map from I P1, and that map is onto by construction, and it's one-to-one because this L was unique. This L has no automorphism. So I mean, the uniqueness takes some sort of work. But I mean, I didn't explain that fully or really that clearly. But but the point, the takeaway, at least for me reading this, which is exactly how much mileage you get out of the fact that the dimension vectors of these modules are roots in the root system, and that for real roots, those dimension vectors are unique. So that's not in Crowley-Bovey's paper, but predates that paper by a lot. And yeah, and that would be something that would be worth understanding. But that allows you to give, I mean, I think this is a really pretty version of this, this feature of the Mackay correspondence. The fact that the resolution C2 mod gamma is a moduli space of representations of this skew group ring, and that these P1s are themselves the modules that are, they have a nice description as modules in terms of the representation theory of that skew group ring. And the rigidity statements for real roots is really what gives you control over the intersections between these spaces. Okay, so maybe I'll stop there.
So at some point you said there was some reader equivalence between Sim2 smash gamma with something else. What's that?
With the pre-projective algebra.
With the pre-projective algebra of affine type.
Of affine type. With the pre-projective, yes, Peters was asking about the Morita equivalence between the pre-projective algebra of affine type and the skew group algebra. That's right.
What's this homological formula?
The homological formula is, I'll write it down. It expresses the relationship between the Euler. It says, I think it's just the statement that the Euler form is the pairing on the root lattice. Let's see, how does Crowley-Bovey write it down? I mean, he writes everything in terms of the, yeah. So he says, so dim x1 mn equals dim hom mn plus dim hom nm.
Oh, this one.
Minus the pairing of the underlying dimension vectors. But I think, this hom, the other order is like x2, so this is basically, yeah. I mean, he doesn't write it in a very conceptual way, but I think this is just the expression that the statement that the pairing on the root lattice is the Euler form. Yeah.
Although actually I'm a bit confused. Like, why is there no x3 then?
I don't think there are any x3s in this category. Peter asked why there's no x3.
Oh, hold on.
Yeah.
Oh, yeah, pre-projective.
Pre-projective algebra, no x3s. It's always 2 Calabi-Yau. Yeah, there's no x3s though. I don't ask about x4s.